you so very much for being here. It's really weird times, and well, it's still good to be together in this kind of non-local weird way. Okay, this is a paper which I could give you the link because we have uploaded already. So I'm just going to put the link in the chat. So for those willing to go into much more details than I'm going to go through this talk. Okay. So this is part of a kind of general approach which we've been working with César and also with Raimundo, and we call it the logos approach. It's a kind of logos categorical framework that we've been working on, but which is also more general with respect to the perspective about what is realism meaning and what is physics as well. So I'm going to give this talk which relates to the notion of quantum entanglement, which is kind of very strange story within quantum mechanics. I think it's a very good, extremely good metaphor of the history of quantum mechanics in the 20th century, and also of its development in the 21st century, and the role played by philosophy there. So let's begin with this. Of course, as Alisa Bokulic and Greg Jager point out, the EPR paper where we first find the notion of entanglement was devised as a kind of ad absurdum proof of quantum mechanics. So the notion is kind of used in a critical way regarding quantum mechanics, and this is very clear in Einstein's reflection about it, but also in Erwin Schrödinger's, in the series, very famous series of papers from 1935. So Schrödinger, for example, says if two separated bodies, each by itself known maximally, enter a situation in which they influence each other and separate again, then there occurs regularly that which I have just called entanglement of our knowledge of the two bodies. The combined expectation catalog consists initially of a logical sum of the individual catalogs. During the process, it develops casually in accord with known law. There is no question of measurement here. So he's thinking about the evolution of quantum mechanics itself. And the knowledge remains maximate, but at the end, if the two bodies have again separated, it is not again split into a logical sum of knowledge about the individual bodies. What still remains of that may have become less than maximal. So the knowledge of the two subsystems changes, it decreases, even very strongly so. One notes the great difference over against the classical model theory, where of course, from known initial states and with known interactions, the individual state would be exactly known. But this points explicitly, quite directly to the aversion of both Einstein and Schrödinger regarding quantum jumps and in general the collapse of the quantum wave function. Albert Einstein is quoted by Everett to have said that I cannot believe that a mouse can bring about drastic changes in the universe simply by looking at it. And in a more ironic way, Schrödinger would state the following: the jokes apart, I shall not waste the time by treatily ridiculing the attitude that the state vector or the wave function undergoes an abrupt change when I choose to inspect a registering tape. Another person does not inspect it, hence, for him, no change occurs. The Orthodox school wards off such insulting smiles by calling us to order. Would we at least take notice of the fact that according to them, the wave function does not indicate the state of the physical object, but its relation to the subject. This relation depends on the knowledge of the subject, the subject has acquired, which might differ for different subjects. and so must the wave function. Okay, so this is clearly an attack against the notion of collapse, but this was not only the point made by Schrödinger, and regarding this, also the representation of the collapse, not only the representation of the collapse, but the representation of quantum mechanics itself was under a huge debate. There is a very interesting meeting that took place in 1927, I think by the end of 1926, so at the beginning of 1927, where Schrödinger went to Copenhagen to meet Bohr. Heisenberg was there, and Heisenberg recalls this meeting, and he describes it in a very well peculiar fashion. I think exposing very clearly the way in which the rhetorics of Bohr worked out, which are very powerful, of course, very efficient. So the story goes that Schrödinger gave a list of very long and detailed arguments against the existence of quantum superposition, against the existence of quantum collapses. On the one hand, the non-existence of a representation in formal terms was one of the points, and another point was the lack of experimental evidence about the existence of collapses. So all these arguments allowed Schrödinger to conclude that the whole idea of quantum terms is sheer fantasy. And what Bohr responded was clearly great and amazing, and kind of very explicit of the way in which Bohr could turn upside down a discussion. So he said to Schrödinger, what you say is absolutely correct, but it does not prove that there are no quantum jumps. It only proves that we cannot imagine them, that the representational concepts with which we describe events in daily life and experiments in classical physics are inadequate when it comes to describing quantum jumps. Nor should we be surprised to find it so, seeing that the processes involved are not the objects of direct experience. So here, Bohr is kind of using this kind of rhetorical technique where he mixes realism and anti-realism in a very convincing way. So he talks about quantum jumps, which were explicitly added as an anti-realist condition, in terms of something really existent, but something which cannot be represented. And at the same time, he uses particle metaphysics in the same fashion, as kind of picture which kind of explain things like his model of the atom, but which, on the other hand, should be considered also just in fictional terms, just as a way of talking. So you have this double way of referring to things, which is very efficient in the case of Bohr. Now, it's not only the application of particle metaphysics, but also the redefinition of the notion of state itself, which is essential to the notion of entanglement. And this was developed by Paul Dirac. And we've written a paper with César, which has been just published, and where we discuss this point in detail. I think it's a very essential point, which shows the inconsistency of the notion of pure state, which grounds the standard account of quantum mechanics. I mean, the notion of pure state is one of the basic notions in standard quantum mechanics. It is taught to students in physics all around the world. And our claim is that this is an inconsistent notion, basically because it's kind of, it has two definitions. One is an operational definition, which is dependent on a basis. So given a quantum state in a state which can be written as a single term in Dirac's notation, there exists an experimental situation. This is a context or a basis, a reference frame, in which the test of it will yield with certainty, this is with probability equal to 1, its related outcome. Now, this definition is a contextual definition. It's a basis-dependent definition. But we also have another definition, which is what we have called trace invariant purity, where there is a shift in the level of representation. Now, Dirac has also used an abstract unit vector in Hilbert space. Now, we're not making any reference to any reference frame, with no reference to a specific basis, which understood as a density operator ρ is a projector, namely where trace of ρ squared is equal to 1 or ρ is equal to ρ squared. Now, this is a general property of rank 1 matrices, which is completely independent of the reference frame. So here we see how we have two definitions which coexist in the literature. I mean, in every paper you see the application of these two definitions within the same paper, and they don't mean the same. As a matter of fact, they are contradictory in a certain sense. So we have problems, of course, with the notion of pure state. And, well, what we would like to discuss in this talk is the way in which particle metaphysics, but also the notion of pure state, and also the notion of collapses, has been related to the present definition of entanglement, the debates about quantum entanglement, the way in which it is discussed, not only in philosophy, but also in physics, in computer science, in all the different fields of this new quantum technological era of quantum information processing. So I was pointing out at the beginning of the talk this strange story about quantum entanglement, which is a story of an absence of this notion for half a century, because since 1935, when this notion was explicitly developed in terms of a Gedanken experiment by Einstein and Schrödinger, there was a complete silence for half a century, mainly because everyone thought that Niels Bohr had solved everything with his famous reply to EPR. So there was nothing else to discuss. Entanglement was a metaphysical or conceptual or philosophical notion which Einstein had introduced because he didn't understand quantum mechanics. He was an old guy and he was not ready for this quantum revolution that was going on. So, as Jeffrey Bubb says, most physicists attributed the puzzling features of entangled quantum states to Einstein's inappropriate detached observer view of physical theory, and regarded Bohr's reply to the EPR argument as vindicating the Copenhagen interpretation. It was not until the 1980s that physicists, computer scientists, and cryptographers began to regard the non-local correlations of entangled quantum states as a new kind of non-classical resource that could be exploited rather than an embarrassment to be explained away. Of course, this is intrinsically related to the debates that were taking place since Bell's famous papers about EPR and the growing interest in foundational and philosophical issues about quantum mechanics. We have to recall that during the 1970s and beginning of the 1980s, it was that philosophy of quantum mechanics began to be considered as a field of its own, a field really worth considering as something taking place on its own ground. And this, of course, is central to understand this development, which during the 90s exploded in terms of a worldwide research in quantum information processing. Now, the way in which philosophers have ever since related to the notion of entanglement is quite well, not so entangled as it could be. Let me say it in that way. As Alisa Bokulic and Greg Jager point, during the last decades, large body of literature has emerged in physics, revealing many new dimensions to our concepts of entanglement and non-locality, particularly in relation to information. Regrettably, however, only a few philosophers have followed these more recent developments, and many philosophical discussions still end with Bell's work. So, regarding the Orthodox definition of entanglement, what's important to point out is the direct reference to particles, right? When we discuss, when we see a paper about quantum entanglement, there is immediately the reference to particles. And yet, it's kind of obvious in philosophy of quantum mechanics that this reference is kind of just a way of talking, because, as a matter of fact, nobody knows really what a quantum particle means, at least not in the sense of classical physics. There is, in the 1990s, already a definition in this sense by Abner Shimony. The quantum state of many particle system may be entangled in the sense of not being a product of single particle states. And another definition used by Alisa Bokulic and Greg Jager: consider two particles, A and B, whose pure states can be represented by the state vectors Ci and Cb. Instead of representing the state of each particle individually, one can represent the composite two-particle system by another wave function, Cib. If the two particles are unentangled, then the composite state is just the tensor product of the states of the components. The state is then said to be factorable or separable. If the particles are entangled, however, then the state of the composite system cannot be written as such a product of a definite state for A and a definite state for B. This is how an entangled state is defined for pure states. The state is entangled if and only if it cannot be factored as in this way. So entangled state is a state that is non-separable, in other terms. So here we begin seeing that the notion of entanglement is intrinsically related to notions which are completely undefined in quantum mechanics, or which have severe problems. The notion of pure state, the notion of particle, the notion of collapse, the notion of separability. Okay, so let's concentrate in factorizability. In the last decades, we've seen a lot of research in this, in relation to this, the possible definition of, in terms of factorizability, and the kind of critical arguments coming around. Because, as Alejandro de la Torre and co-workers have proven, for any system in a factorizable state, we can find different degrees of freedom that suggest a different factorization of the Hilbert space, where the same state becomes entangled. And what they're feeling, and co-workers, for a given quantum state, it is our freedom of how to factorize the algebra to which a density matrix refers. Thus, we might choose. Via global unitary transformations, we can switch from one factorization to the other, where in one factorization the quantum state appears entangled, however, in the other, not. Consequently, entanglement or separability of a quantum state depends on our choice of factorizing the algebra of the corresponding density matrix. Of course, this is very, very problematic. So until what time do I have, Raoni? I have until
you have more like 15 minutes or so.
15 minutes around, huh? Okay. I'm going to speed up then. So realism. So John Ehrman has characterized the problem that relates to this factorizability question relating to quantum states. So for the realist, the kind of entanglement that should be concerned with entanglement over subalgebra that correspond to real as opposed to virtual or fictitious subsystems. And this is obviously the opposite from anti-realism, anti-realists who really are not interested in considering entanglement as a real interaction between systems. So we get to the first definition of non-separable relativism. Given a pure state, the existence of entanglement is relative to the chosen factorization. Consequently, the same state will be entangled or not, depending on the factorization that is being considered. Okay, now, so we get to a point where we can speak about relativism, right? And the main physicist, the main figure who introduced relativism within quantum mechanics is clearly Niels Bohr, first within the double slit experiment and the relativization of representations, waves, and particles to describe a state of affairs, depending on the choice of the measuring setup. And then, of course, in EPR's reply, where the definite properties of the quantum states were defined also in terms of the measurement setup. So there is here a kind of a shift, very essential shift from objectivity, and I'm thinking of objectivity in the Kantian terms, or as a moment of unity, at the possibility of a representation of a moment of unity, which is intersubjective as well. So objectivity implies intersubjectivity. And mere intersubjectivity as the communication of observations between subjects. In the case of Bohr, well, he used the term objective as intersubjective, generating what I believe is a widespread confusion within philosophy of quantum mechanics regarding the term objective. In the case of Bohr, he points out the description of atomic phenomena has a perfectly objective character, in the sense that no explicit reference is made to any individual observer, and that therefore no ambiguity is involved in the communication of observation. Another quote by Bernard Espagnat pointing out that this is clearly the way in which Bohr identified objectivity with intersubjectivity. Now, to clarify this, I would like to take a moment to discuss this difference between objectivity on the one hand and intersubjectivity on the other. So in the Kantian sense, objectivity means that there is a moment of unity, in the case of Kant, an object, which is described independently of any subjective perspective. And we could say that this is the main idea of invariance in physics as well, because invariance, the transformations laws of which are present in classical mechanics, electromagnetism, relativity theory, are transformation laws which allow us to consider different representations of the same state of affairs. So the state of affairs is the same, even though the representation from different reference frames can change. But because we have the transformation that translates what is the specific values of the properties, let's say the velocity of a particle, from different reference frames, we can claim that the object itself has a given property, such as velocity, even though this value is not the same for every reference frame. Now, in the case of intersubjectivity, well, if we are talking just about observations, well, there is no common reference. So this is a kind of essential difference between what I would consider a precondition for realism, the objective reference to an object, and the mere intersubjective relations between the observation of measurement outcomes. Okay, so just two quotes pointing out to what I believe has been a refundation of physics in the 20th century, mainly due to Bohr on the one hand, and also to positivism on the other hand, to pragmatism, to instrumentalism, a conception of physics in terms of what Mach would call an economy of experience, or to quote Bohr, physics is to be regarded not so much as the study of something a priori given, but rather as the development of methods of ordering and surveying human experience. In this respect, our task must be to account for such experience in a manner independent of individual subjective judgment and therefore objective, in the sense that it can be unambiguously communicated in ordinary human language. Now, there is a very interesting work by Barnum and co-workers, which have developed a generalized notion of entanglement. Now, in the work of Barnum et al., there is a shift from the factorizability definition of entanglement to a definition dependent on observables. I quote Barnum and Viola. The standard definition of quantum entanglement requires a preferred partition of the overall system into subsystems, that is, mathematically a factorization of the Hilbert space as a tensor product. Even within quantum mechanics, there are motivations for going beyond such subsystem-based notions of entanglement. The key idea of generalized entanglement is that entanglement is an observer-dependent concept, whose properties are determined by the expectations of a distinguished subset of observables of the system of interest, without reference to preferred subsystem decomposition. Generalized entanglement of a quantum state relative to the distinguished set may then be defined without reference to the composition of the overall system into subsystems. And this is the main claim by Howard Barnum. Entanglement is an inherently relative concept, whose essential features may be captured in general terms of the relationship between different observers. So of course this points to a kind of anti-realist understanding of entanglement, and to contextual relativism, the fact that given a pure state, the existence of entanglement is relative to a preferred subset of observables. Thus, the same state will be entangled or not depending on the choice of the specific subset. I mean, clearly from a physical perspective, this presents a difficulty, because if we are believing that there is a state of affairs and we think that entanglement is a kind of property of that state of affairs, then that property cannot depend directly on our specific choices. I mean, it cannot exist or not exist depending on the choices I make. Now, there are many problems with orthodox entanglement at this moment. I mean, there is a huge list of problems in every presupposition made by the definition, the orthodox definition given in the literature. Now, this is just a very long list of technical problems regarding the limitations to using a violation of Bell inequalities as a general measure of quantum entanglement. I believe that, I mean, the relation between Bell inequalities and quantum mechanics is also quite misunderstood in general, especially by physicists, mainly because Bell inequalities are a statement about classical probability theory, a statement which was made, as Pitowski has clearly made a point, 1 century before Bell even wrote his paper by Boole. So Boole was talking about the general conditions of classical experience, and Bell inequalities are just a limit for classical correlations. So what Bell inequalities are presenting is a limit of classical correlations, but they don't impose quantum correlations. And that's something that has been is kind of misunderstood today. I believe it's a very essential point. The fact that because you have violation of Bell inequality, that doesn't imply any quantumness, essentially. There is also the problem with non-separability, with the notion of separability. There is a kind of very uncritical application of separability. Albert Einstein already pointed out when he was using this notion in the EPR paper, that this notion is nowhere to be found in quantum mechanics. There is no clear definition of what separability is within quantum theory, at least if we consider the formalism of quantum mechanics. And this is kind of already very well understood in terms of the way in which Hilbert spaces and vectorial spaces relate between each other, and the fact that the product of two rays generates a whole plane. It's not just the sum of the two rays. And this is a very basic way of exposing the fact that the conjunction of systems in the way we think classically has nothing to do with the way in which conjunction acts in quantum mechanics. You know, Rob Clifton has a very interesting set of papers discussing this with respect to the B-orthogonal decomposition, which is a very basic aspect of a very basic condition of separability within entanglement, and also Dix and Luberding have shown that the labeling in the factorization is unrelated to the existence of particles. So this is just a mathematical way of describing things, but it's not intrinsically related to the existence of particles. And of course, we have the famous proof by Dirk about the non-separability of quantum states in the context of quantum logic, the non-separable theorem by Dirk from 1981. And of course, I mean, the extension to mixed states also generates a lot of problems as well, because as John Ehrman points out, since different convex linear combinations can produce the same mixed state, it is not easy to determine whether or not a given mixed state is indecomposable. So we have not only problems to measure what entanglement is, we even have problems to define what entanglement is in a given state of affairs. So this is really problematic for the technology that is being developed today, certainly. I mean, and philosophers would have a lot to say about this, I believe. And of course, I mean, the collapse of the quantum wave function, which is a kind of very basic aspect of standard quantum mechanics. I mean, it's still today, it lacks completely a reference to the formalism, to the mathematical formalism, and it has found no experimental evidence. No? Collapses constitute, says Dennis Dix, a process of evolution that conflicts with the evolution governed by the Schrdinger equation. And this raises the question of exactly when, during the measurement process, such a collapse could take place, or in other words, of when the Schrdinger equation is suspended. This question has become very urgent in the last couple of decades, during which sophisticated experiments have clearly demonstrated that in interaction process on the submicroscopic, microscopic, and mesoscopic scales, collapses are never encountered. So why are we still talking about collapses? Okay, so the Logos approach to quantum mechanics is an attempt to produce an objective representation of quantum mechanics in invariant objective operational terms. And by this, what is meant is that in a very classical way of considering states of affairs in physics, there has to be invariant. There has to be an invariant character in the mathematical formalism. And this invariant aspect of the mathematical formalism, which allows us to describe a state of affairs independently of reference frames, has to have a conceptual counterpart, which is objective, in the sense in which I described before, in the Kantian terms, in the sense of having a conceptual moment of unity, which allows us to make reference to the same from different empirical subjective viewpoints or perspectives. So this has to be, and of course, I mean, there has to be an operational content of this. I mean, we cannot just add metaphysical pictures or interpretations or stories about what quantum mechanics is without making these links, without connecting the concepts with the mathematical formalism and with its operational content. I mean, this is very Einsteinian in the sense of relativity theory. Einstein made exactly this explicit work in relativity theory, in special relativity theory, with respect to the notion of simultaneity. So the existence of a preferred reference frame or preferred basis is completely unacceptable for realists. It should be completely unacceptable for realists. Because in physics, all reference frames must provide an equally acceptable representation of the same state of affairs. Changing a reference frame cannot change the state of affairs. This is completely unacceptable. And this is, of course, what was broken in the case of Bohr first, and then the formulation by Dirac and von Neumann. And analyzing the mathematical formalism, we reached the conclusion that quantum mechanics does not talk, as a matter of fact, about single measurement outcomes, but about intensive values. No? So there is no need of making reference to collapses or projections, because the Born rule is the rule that provides this invariant content if you relate the Born rule to intensive values instead of measurement outcomes. And as a matter of fact, I mean, if you check the history of quantum mechanics, the development of quantum mechanics was from considering what was observed in the lab by Heisenberg. And what was observed in the lab at that time was not measurement outcomes. It was intensive values. And it is through the invariance of intensive values that matrix mechanics was developed. The story of how the reference from intensive values changed to measurement outcomes is the history of the path from matrix mechanics, first to Schrödinger's wave mechanics, and then to Dirac's formulation.
Sorry, Chris, I have to interrupt you because otherwise we'll have little time for a discussion. Would you like to conclude?
I will close the talk. So from this perspective, we have been able to bypass, you can easily bypass Koch and Specker theorem and generate an objective reference to a quantum state. And the way you do this is basically, well, you just consider an abstract vector in Hilbert space, you consider the projection operators, and you apply the Born rule. And it's the Born rule itself which allows you to generate this invariant between different contexts. So if you just refrain from discussing about measurement outcomes, then it is possible to restore objectivity to the formalism of quantum mechanics. Now, well, I would just give the trailer of the paper, because what we've done with César is, well, we redefine the notion of entanglement in what we believe are objective terms. And this is in terms of the potential coding of intensive relations, which are also linked to the effective relations that appear in measurement outcomes. But what has been bypassed in the literature is this relation between intensive values, which is essential. So we've given a new definition of quantum entanglement and also of relational separability and intensive correlations. We have, instead of just one single definition, which depends on separability, on particle metaphysics, on collapses, a definition which is given to wave functions in a Hilbert space. Then if they are intensively and effectively related, then there exists quantum entanglement. That's the way in which we have provided this definition. And what is very interesting, I have not been able to reach the part in where I was going into relativism, is the fact that this allows us to bypass completely, through two theorems, the factorization relativism imposing in the Orthodox notion of entanglement, and also the relativistic dependence of observables as well. So with this new definition that we are giving, we hope to provide an objective way to referring to entanglement about a state of affairs without the need of using this dependence on choices, on subjective choices. Thank you very much.
Thank you, Chris. Thank you, César. Oh, we have a little time for questions now. Décio already raised his hand. Please, if you have a question, use the raise hand function in the bottom right, or type it in the chat question. So go on, Décio, please.
You are muted, Décio. We're not listening.
That's
you are muted.
So sorry, people.
Okay.
I was thanking you so much for the talk, but I will be brief. Just one question concerning the relativism of the quantum state. It's a very interesting idea. But you said that in some contexts, some state can be factorized, and in other contexts, it cannot be factorized. You mentioned Alejandro de la Torre and Barnums et al. And so on. If I think I got the concept in this way. But how can you know that you are speaking about the same state? Because if you are in the same Hilbert space, the answer is easy, because you can just to change bases. But if the context, as you said, the human experience and so on, you mentioned that, it's really difficult to know that you are speaking about the same state. Once factorized, in another case it is not factorized. How do you explain that? Was I clear?
Yeah, I'm not sure I understand the question.
The question, I repeat the question. You have a state which, as you said, in one context it is factorizable, in another context it's not factorizable.
Yeah.
I am sure.
Yeah.
How do you recognize that the state is the same one?
Oh, because it's the same vector. You start with your state.
Well, in the same vector space, then you are just changing bases.
No, yeah, of course, but I mean, you begin with you begin with a vector in Hilbert space, a specific vector, and now
then you change bases.
I mean,
you are in the same Hilbert space.
The separability depends on the factorization, on the factorization.
Then it depends on the basis of the Hilbert space.
Yeah.
Yeah.
You change basis.
That's the result.
So if you change basis, something that is entangled becomes non-entangled, and vice versa.
Okay.
That's the result.
Okay. Thank you so much.
Maybe César, you can say it in more.
Yeah. You explained it. Yeah. No, it's clear, because you are keeping in the same Hilbert space.
Yeah.
Just changing the basis.
Yeah.
Okay, that's no problem. Thank you so much.
Thank you, Décio.
It's okay.
Now, Otávio. You are still muted, Otávio.
Sorry, there are too many windows here. So thanks, Christian, for this really interesting talk. I had a question that was actually similar to Décio's, and you clarified that to me. So let me just then ask something about the earlier discussion about realism and objectivity, right? So I applaud the project of finding an objective notion here. My question there is the objectivity that you can get a fact from a result from the choice of the relevant mathematical framework? That is, is the relevant trick that you're offering, does it become objective because given the specific mathematical devices that you are using, or it's a feature about something in the world?
Okay, yeah. So basically, I would say the task of a physicist, and I'm taking a realist standpoint, which is not mainstream, of course. I mean, the task of physics is to generate representations which are invariant, objective, and operational. And by this, I'm thinking of physics as in the way that Heisenberg, at the beginning of the 20th century, thought about physics. And this was something very popular at the time. So you have a mathematical formalism, a conceptual framework, and a field of phenomena. And these have to interrelate. Mm-hmm. It's like a system. And so from the mathematical formalism has to be invariant. And the counterpart of this mathematical formalism being invariant is that the conceptual scheme that talks about this mathematical formalism has to be objective in the Kantian sense, not in the sense of observation, of single observation, but in the sense of having a moment of unity. Let's take just an example, like electromagnetism. In electromagnetism, you have Maxwell's equations. Then you have the notions of the concepts of electromagnetic wave, of field, of charge, and then you are kind of, the physicist is able to relate the conceptual part with the mathematical part, and also to phenomena. You can test operationally the mathematical part in quantitative terms, and you can test experimentally in thought experiments what goes on in the conceptual part. And quantum entanglement is an excellent example of this, of how this works. Because, I mean, the notion of quantum entanglement is in fact derived by Schrdinger and Einstein, following this way of understanding physics. It's kind of developing a concept which you can find in the mathematical formalism, and then relating it to experience and deriving conclusions from it. And I think that the way in which quantum mechanics has been approached, well, it's kind of sad, because we've been for half a century without understanding the deepness of quantum mechanics, because instrumentalists and positivists and Bohrians thought that that it was enough to talk about measurement outcomes, right? So
right, no, and that's very clear. I fully agree. The concern was that you may have objectivity that you get by the choice of the mathematical devices, right? Because you have the invariances there, right? But they need not translate into the appropriate concepts, right? To use the way you are.
You have to create them. You have to be able to use them.
Right, but then how do you know that you're referring to the right things, right? So, for example, set theories, in that sense, you can form all kinds of invariances and express them with the theory, which will force you to settle certain things conceptually. That may not be appropriate for the phenomena you're trying to handle. So it's in that sense.
Yeah, I see your point, but I'm not taking as a standpoint a kind of scientific realist approach. Mm-hmm. So I do believe that physical theories mirror reality. I don't think that's a very good way of understanding realism. I mean, it failed, actually. I mean, it's a failure. That doesn't work. Mm-hmm. I think of theories. I mean, I'm going to give you a metaphor, but it's kind of net. It's not a mirror. It's a net. You create a net within reality, because you are within physics. So you create a net within physics, and you go and try to catch within physics certain singularities which are exposed in experience. in measurement. So in measurement, then you check out, oh, okay, this theory really captures something.
Right.
But this should not be understood as saying, that means that what my theory says is exactly what reality is.
Right.
That's not it. Now, certainly, well, I think we agree on that point.
Yeah. No, fully
Thank
so.
you, guys.
Thank you.
Unfortunately, we don't have the time for Dieter's question, so let's thank Christian and Cesar once again.